Welcome, students. This is a quick summary of chapter 2.3 on the probability function. Last time we have studied concepts of experiment, sample space, sample outcome, event, and so on. Today we will be concerned with assigning probabilities to experiments outcomes. First of all, probability is a real valued function that assigns a number from 0 to 1 to an events in our sample space. So let's assume here we have our sample space. Inside of sample space, we have some subset of it, which we call an event. Let's call it event A. Then probability is a function that takes an A as an input and assigns it to a number from 0 to 1. Let's take a look at the following example. Let's assume that our experiment consists of throwing a die single time. Then my sample space consists of outcomes from 0 to 6. So numbers from 0 to 6. 1, 2, 3. Here's 4, 5, and 6. Let's try to find probability of an event when I get an even number. This event is defined as a collection of the following outcomes: 2, 4, and 6. Then probability is a function that is going to assign an event of an even number, of getting an even outcome on our toss, a number in that case which is equal to 1/2. All right. Okay, so Kolmogorov is the father of modern probability. What he did is he collected all the rules regarding our probability function and squeezed into 4 basic axioms that are necessary and sufficient to characterize our probability function. So in a case when our sample space is finite, we even need only 3 axioms. Now let's take a look at them. All right, 1 second. All right, so here are our 4 axioms. In the case when our sample space S is finite, for instance, as our example here, then we only need the following 3 axioms, and we need axiom 4, which is very similar to axiom number 3 in a case when our sample space S is infinite. Okay, let's go over this. So axiom number 1, it states that probability of an event cannot be negative, or probability of A is greater or equal than 0 if A is an event. A pretty straightforward axiom. Next one is probability of sample space is equal to 1. So in other words, no other outcome outside of those defined in your sample space are possible. If we look at an experiment where we are tossing a coin, if you define heads and tails in your sample space, let's say tails with 0.5 probability and heads with 0.5 probability, then no other outcome possible. If you want to define an event where your coin lands on its side, you have to define it in your sample space. Okay. Now, axiom number 3, if we have 2 mutually exclusive events, we know that 2 events are mutually exclusive if their intersection is an empty set, then probability of union of those 2 is equal to the sum of their individual probabilities. All right. Now, those three axioms are enough to characterize our probabilities function in the case when S is our sample space is finite. In the case when our sample space is infinite, we have to add axiom number 4, which is similar to the previous one. So if we have events from A1, A2, and so on, so infinite list of events here, if all of these are mutually exclusive or a intersection of AI with AJ is an empty set, if I is not equal to J, then probability of union I running from 1 to infinity of those events AIs can be expressed as the sum of their individual probabilities. I from 1 to infinity. Unfortunately, this axiom number 4 does not, even though it's very similar to axiom number 3, it does not follow from previous axiom. So we have to add this force in the case when our sample space is infinite. All right, now let's take a look at the following useful theorems that follow from these axioms. So theorem 2.3.1. We'll be using this when solving various problems. Probability of complement of event is equal to 1 minus probability of an event. All right, let's prove it. So by definition, A complement union with A is a whole sample space. So we have our event A, and everything that is outside of our event, union of those two is the whole sample space. Then probability of A complement union with A might be expressed as probability of A complement plus probability of A. Since those two, A complement and A, are mutually exclusive by definition. So this sum is equal to 1. So this sum is equal to probability of sample space, which is equal to 1. So probability of A complement is equal to 1 minus probability of event A. All right, next theorem. Theorem 2.3.2. Probability of an empty set is equal to 0. All right, so by definition, we know that empty set is a complement of everything, is a complement of sample space. So probability of empty set is, by our first theorem 2.3.1, is then equal to 1 minus probability of sample space. Or let me be a bit more clear. So probability of empty set is equal to probability of S complement, which is 1 minus probability of sample space, which is 1 minus 1, which is 0. All right, next theorem. Theorem 2.3.3. If A is a subset of B, then probability of A is less or equal than B. All right. Now, let's take a look at the following Venn diagram. Let's say we have event A. Let's say this is event B, and we have smaller event A, which is a subset of event B. All right, now let's take a look at an event B. We can define it as a union of the following two. A union of A with union of everything that is inside of B but not in A, which can be defined as A complement intersection with B. All right, let me show you in more detail how I got this intersection over here. So if we have event B and event A inside of it, let's take a look at A complement. So I will color it in red, vertical lines. A complement is everything that is outside of A. And let's take a look at B. B will color it in blue, horizontal lines. Now, intersection of A complement and B is the following region where we have both vertical red and horizontal blue lines. So this is everything that is inside of B, but outside of A. Okay, great. So B can be defined as union of those two. And as we can see from our Venn diagram, those two are mutually exclusive events. So by axiom, our axiom number 3, the probability of B is equal to probability of A plus probability of A complement intersection with B. All right, now we have to show that probability of A is less or equal than probability of B, since from axiom number 1, we know that probability of an event cannot be negative, meaning that we have proven our theorem number 2.3.3. Okay, since this is non-negative. Now, theorem 2.3.4. For any event, a probability of an event is less or equal than 1. We know that by definition, any event is a subset of sample space, which then follows from our previous theorem that probability of A is less or equal than probability of S, which is equal to 1. All right. Now on to the next theorem. Theorem 2.3.5. Let's assume we have following infinite list of events, A1, A2, and so on. Those are mutually exclusive events. So intersection of AI with AJ is an empty set for I not equal to J. Then probability of, oh, I'm sorry, guys, this is not an infinite set of events. This is these are events A1 through AN. Okay, so this is a finite collection of events A1 to AN. Then if we are looking at a probability of union of those AIs from 1 to N, it can be expressed as the sum of their individual probabilities. So the sum of AIs I from 1 to N. So this is similar to axiom number 4, but in this time we have a finite collection of events from A1 from 1 to N. Okay, let's prove it. We prove it by induction. I will not go over too much detail. In the case when N is equal to 2, this is straightforward axiom number. This is straightforward axiom number 3. In the case when N is equal to 3, A1, A2, and A3, we can call, we can assign to the union of events A1 and A2 a special name and call it as some other event B. Then this is again is going to be true by our axiom number 3. In a case, so this is our induction base. Now let's take a look at our inductive step. So in the case when we have a union of events from A1 through, let's say, AK plus 1, in that case, again, we can define a union of events from A1 to AK as some other event, let's call it C. Then this again is going to be true by axiom number 3. And the proof that union of the probability of union of A1 through AK is equal to the sum of individual probabilities is our induction hypothesis. Okay, so pretty straightforward induction. All right, now on to theorem 2.3.6. Okay, guys, you guys are probably familiar with this one from Venn diagrams. In the case when we have probability of union of two events A and B, those are not necessarily mutually exclusive, then probability of this union might be defined as probability of A plus probability of B minus probability of their intersection. Okay. Let's take a look at the following Venn diagram. Let's assume we have event A here, event B. Okay, now let's take a look at an event A. We can define event A as the union of A intersection B. So this red area, union of it with A intersection with B complement, which is defined as blue area here. All right, let me show in greater detail why this is blue region here is defined as A intersection with B complement. So again, we have our sample space here, event A, B. First of all, let's color B complement in blue vertical lines, in blue red lines. I mean vertical red lines, sorry. So now we are going to color A in blue. So A is in horizontal blue lines. All right, now let's find a region where we have both vertical red and horizontal blue lines. So intersection of this happens in this region. So everything that is inside of A except its intersection with B, right? We can do the same for B. So B can be defined as union of A intersection with B with A complement intersection with B. All right, so this is very similar to event A. All right, now if we take a look at those two regions, here we can see that these two events are mutually exclusive. So probability by axiom number 3, probability of A might be defined as probability of A intersection with B plus probability of A intersection with B complement. And similar argument for event B, probability of B is defined as probability of A intersection with B plus probability of B intersection with A complement. All right, now let's sum these two. So we are going to have probability of A plus probability of B is equal to probability of, let me write it down the following way, probability of A intersection with B complement plus probability A intersection with B plus probability B complement, B intersection with A complement. B intersection with A complement. And then we have another probability of A intersection with B. So plus probability of A intersection with B. Okay, let's merge this together in the following square brackets. Okay, now let's take a look at that expression inside of the brackets here. So we have probability of intersection of A with B complement. So this is blue region over here. Everything that is inside of B but outside of B. Everything that is inside of A but outside of B. Next, probability of A intersection with B. So this first event is in blue on our Venn diagram over here. Next, we have intersection of A and B. This is a region in red, corresponding to the intersection of events A and B. And last, we have everything that is inside of B but outside of A. So B without its intersection with A. Let's color it in green. So this is area. Let's color it in purple. This is area in purple over here. So we can see that all the three events are mutually exclusive, and they compose our union of two events A and B. So this can be defined as probability of union A and B. Right? 1 second. So this can be defined as a probability of union of A and B, which is equal to probability of A plus probability of B. And we have probability of their intersection. Let's have left outside of brackets here. All right, so we have proven that probability of union of two events A and B can be defined as probability of A minus probability of A intersection B plus probability of B. Okay, great. Now let's try to use the theorems to solve a couple of examples. All right, so example 2.3.1. We have two events A and B. Probability of A is 0.3. Probability of B is 0.5. Probability of their union is 0.7. Let's find probability of their intersection. So from previous theorem, we know that probability of union of A and B is equal to probability of A plus probability of B minus probability of their intersection. Now, if we express probability of their intersection, then probability of their intersection is going to be equal to probability of A plus probability of B minus probability of their union. So probability of their intersection is then equal to 0.5 plus 0.3 minus 0.7. So it is equal to 0.1. This is part A. Part B, let's find probability of union of complements of A and B. Let's try to visualize this union here. So here's A, here is B. First, I'm gonna color in red if this is A, if this is B. First, we are going to color in red A complement in vertical red lines. Everything outside of A. Now we are going to color B complement. So B complement is everything that is outside of B in blue, horizontal lines. All right, now we have to take a union of this. So union of this is going to be whole sample space outside of this intersection over here. Okay. Now we can find a probability of union of those two events as a whole sample space 1 minus probability of intersection of A and B, which is equal to 0.9. Since probability of the intersection, we found in part A, which is equal to 0.1. All right, now part C. Let's find probability of intersection A complement with B. Probability of A complement with B. All right, so from the proof of our previous theorems, we know this is a region inside of B, except for intersection of it with A. So this should be equal to probability of B minus probability of its intersection with A. So probability of B here is equal to 0.5, so that should be equal to 0.4. Or you can visualize this as follows. Here's A, here's B. B intersection with A complement. A complement is in red vertical lines. Then B is in blue. So intersection of these two will be everything that is inside of B, except for its intersection with A. All right, now on to the next example. Okay, let me copy this one. So we have a student who is applying to two colleges, X and Y. Probability of being accepted at college X is 0.7. Probability of being accepted at college Y is 0.4. Also, he suspects there is 75% chance that at least one of his applications will be rejected. So we can define this as follows. Let's take a look at Venn diagram. Here's X, here's Y. So this intersection of X and Y here is a region or event where he gets accepted by both colleges. So we are looking for the region where he will be rejected by at least one, meaning that it is everything outside of this intersection here. So this is defined as probability of X intersection with Y complement, which is equal to 75%. Right? So instantly from here we can find that probability of intersection of X and Y is equal to 0.25. All right, so a question is, what is the probability that he gets at least one acceptance? Let's come back to our Venn diagram here. Probability that he gets at least one acceptance. So at least one acceptance can be defined as union of X and Y. All right. So we know by definition, we know by our theorem that probability of union of two events can be defined as probability of X, probability of Y, minus probability of their intersection. So this is 0.7 plus 0.4 minus 0.25, so which is equal to 0.85. All right. Okay, guys, this will be it for our summary on chapter 2.3. I'll see you next time on a summary for chapter 2.4. Have a good day.